Imagine a single particle of light. Now, stretch it. Not like gym stretch. Not like, I'll just touch my toes and make sound effects stretch. Stretch it until one wave is bigger than your house, bigger than your city, bigger than Earth, bigger than the solar system. Keep going until this photon is so ridiculously huge that the observable universe is basically sitting inside one lazy wave. At that point, you have to ask a very fair question. Is that still a photon? Or did we just invent the universe's slowest Wi-Fi signal? Now do the opposite. Take the same photon and shrink it. Give it more energy, then more, then more. Make its wavelength smaller than a virus, smaller than an atom, smaller than a proton. Keep going until small itself starts sweating. At some point, physics looks at you and says, "Boss, don't make me call gravity." Because if you try to make a photon too small, you may not get a smaller photon. You may get a tiny black hole. So today we're asking a question that sounds like it belongs in a child's science fair, but actually leads to the edge of modern physics. How big can a photon be? And how small can a photon be? Light looks simple. Flip a switch, room bright. Done. But if you push one photon to the extreme, it takes you from the edge of the universe to the edge of reality itself, which is a lot of drama for something that also helps you find the bathroom at 2 a.m. Before we start abusing photons for entertainment purposes, we need to clear up one thing. A photon is not a tiny glowing marble. I know, disappointing. Every animation has lied to us. Mine will also lie, but at least I'm telling you first. A photon doesn't have a little hard surface. It doesn't have a tiny body. You can't put it under a microscope and say, "Ah yes, this one is medium size, maybe XL." When people casually talk about the size of a photon, they usually mean its wavelength. That means the distance from one peak of the wave to the next peak. Think of it like ocean waves. If one wave peak hits the beach and the next peak is 10 meters behind it, the wavelength is 10 meters. Light is not literally ocean water, but it does behave like a wave of electric and magnetic fields. And that wave can be short, long, extremely short, or so long it starts feeling personally unreasonable. Visible light, radio waves, microwaves, X-rays, gamma rays, all of them are light. Same family, different wavelengths. Radio waves are the chill cousins. Long wavelength, low energy. Gamma rays are the intense cousins who show up to a birthday party and somehow break the furniture. So the question becomes, how long can that wave get before it stops making sense? And how short can it get before the universe files a complaint? Let's start with the light we actually see. Visible light has wavelengths around 400 to 700 nanometers. A nanometer is 1/1000th of a meter, which is a fancy way of saying very tiny, and also a word people use when they want to sound employed. Blue light is on the shorter side. Red light is on the longer side. Green is in the middle, being emotionally stable. A green photon has a wavelength of about 500 nanometers. That is much smaller than the width of a human hair. In fact, a human hair is tens of thousands of nanometers wide. So visible light is tiny. But now let's zoom out. Microwaves, the ones used in your microwave oven, have wavelengths around centimeters. That's already much bigger than visible light. This is why microwave ovens don't cook your food by sending tiny laser bullets into your samosa. They use electromagnetic waves with just the right energy to jiggle certain molecules, especially water. Now go bigger. Radio waves can have wavelengths of meters, hundreds of meters, even kilometers. FM radio? Around a few meters. AM radio? Hundreds of meters. That means when you listen to a song on the radio, the wave carrying that song may be bigger than your apartment building. Your heartbreak song is literally arriving on a wave the size of a cricket ground. Romantic, but also slightly over-engineered. And here's the first surprising thing. In basic physics, there is no neat maximum wavelength for a photon. If you make an electric charge wiggle slowly, you produce a low-frequency electromagnetic wave. Lower frequency means longer wavelength. Wiggle it even slower, the wavelength gets even longer. So why don't we just create a photon with a wavelength of 1 light year? Because practical life enters the chat. To make a wave efficiently, you usually need an antenna that is related to the wavelength. Not exactly equal, but the antenna size matters. If your wave is hundreds of kilometers long, your equipment starts becoming less like a gadget and more like a geography problem. At some point, your radio transmitter is no longer on Earth. It is Earth. And Earth, as a general rule, is not a convenient accessory. Also, our atmosphere gets involved. The ionosphere, an electrically charged layer high above us, reflects many low-frequency radio waves. That is useful for long-distance radio communication, but it also means Earth is not a clean laboratory for all possible wavelengths. You ask, how big can a photon be? And the first answer is not quantum gravity, it's, sir, your antenna doesn't fit. That is what I love about physics. Sometimes the great mystery of the universe is blocked by atmosphere, budget, and hardware availability. But let's leave Earth. No atmosphere, no buildings, no angry neighbors asking why your antenna crosses 3 districts. Let's go to deep space. Now the photon can get much, much bigger. The Planck length is about 1.6 times 10 to the negative 35 meters. That is written like this: 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000016 meters. I may have missed a zero. That's fine. At this scale, even the zeros are tired. This number is so small that normal comparisons become useless. If an atom were blown up to the size of the observable universe, the Planck length would still be roughly atom-sized inside that blown-up atom. Now, important warning. The Planck length is not necessarily the smallest pixel of space. People often say that, but it's a bit too simple. It's better to say the Planck length is the scale where our current theories stop being reliable. General relativity explains gravity and spacetime beautifully at large scales. Quantum mechanics explains tiny particles beautifully at small scales. But at the Planck scale, both theories are needed at once, and they do not cooperate nicely. It's like inviting 2 brilliant experts to the same meeting, and both of them start explaining why the other one is using the wrong PowerPoint. So if we make a photon with a wavelength near the Planck length, its energy becomes enormous. Not big battery enormous, not electricity bill after running AC all summer enormous, Planck scale enormous. At that point, the energy of the photon is so concentrated that gravity becomes important. Remember, energy gravitates. Even a photon, which has no rest mass, carries energy, and energy can curve spacetime. So if you pack enough energy into a small enough region, gravity says, "Thank you, I'll take it from here," and you may form a tiny black hole. A black hole made from light is called a Kugelblitz, German for ball lightning. Physics really said, we are inventing a terrifying theoretical object. Let's give it a name that sounds like a villain's dessert. So far, the question sounds simple. Biggest photon, very long wavelength. Smallest photon, very short wavelength. But the real answer is more interesting. At both extremes, the photon is not the only thing being tested. On the large end, the photon becomes bigger than the observable universe. Then the problem is not light. The problem is the size and age of the universe. You can't fit a complete wave inside the region we can observe. It's like trying to judge a movie after watching half a frame. Plot was slow. You didn't watch the movie. You saw 0.0001 seconds of a curtain. On the small end, the photon approaches the Planck length. Then the problem is not light either. The problem is space-time. Our normal idea of distance may stop working. Quantum fluctuations of space-time could become important. The smooth background we use to measure wavelength may no longer behave like a smooth background. It's like trying to measure the length of a road while the road is boiling. At that point, asking, what is the wavelength, may be like asking, what is the exact shape of smoke? You can still discuss it mathematically. You can still build theories, but ordinary intuition is gone. This is why photons are such a beautiful way to tell this story. A photon feels simple. It is the thing from a bulb, a screen, the sun, a laser pointer, your phone camera, your TV remote, your Wi-Fi router. Light is everywhere. But when you ask, how big can one photon be? The answer takes you to the cosmic horizon. And when you ask, how small can one photon be? The answer takes you to quantum gravity. That is insane. That is like asking, how tall can a ladder be, and ending up discussing the legal structure of heaven. A photon is not just a particle. It is a messenger that touches the limits of measurement itself. So here's the clean answer. The biggest meaningful photon could have a wavelength roughly comparable to the observable universe, about 93 billion light-years across. Bigger than that, and it may stop behaving like a normal wave we can actually observe. It becomes more like an almost constant field across everything we can see. The smallest meaningful photon may be near the Planck length, about 1.6 times 10 to the negative 35 meters. Smaller than that, and our current physics can no longer confidently tell us what smaller even means. The energy becomes so extreme that gravity and quantum mechanics collide, and the photon may collapse into something more like a microscopic black hole. So photons don't really have a neat size limit. The universe has limits. On one end, the cosmic horizon. On the other end, the Planck scale. Light simply exposes both. That is the big twist.